Let's rock and roll.
Okay, so the title of our talk today is called Law Enforcement, Fraud Detection, and Social Networks. Why those two use cases? I don't know, they seem cool. There are lots of other use cases for graph databases, but yeah. It's tangentially related to my experience at my previous employer. They were a Neo4J implementation company that later rolled out or is still rolling out their own product. That's like a visualization tool and some other stuff for Neo4j. It's called Hume. You can find them if you Google them. They're called GraphAware. So yeah, let's go forward. Okay, so this is what we're going to be talking about. First, just like a higher level overview, what even is a graph database, what is Neo4j, and just a short talk about Cypher, which is the query language that Neo4j uses. And then in part two, we're going to take a look at these two use cases. What's the basic problem definition and how do graph databases help solve that problem? So, okay, first we're going to take a look at what is a graph in our context here. So it's a concept from discrete mathematics. And so they're usually being used to solve problems such as finding the shortest path. We have the example of the traveling salesman problem also, and the seven bridges problem, which is probably one of the earliest problems approached as a graph, the seven bridges of Königsberg. So we're talking about geospatial optimizations. So I guess your Google Maps uses this. Also, if you, let's say you have a logistics company, you need to do deliveries, they should plot out, how to visit, like the traveling salesman problem, how to visit all these places while wasting either the least amount of time or fuel, whatever, which way you design your model. The graphs pictured here, the first one is an example of a undirected but weighted graph. So you see the lines between the nodes have numbers on them. These are weights, so they're not all equal. And the second example actually comes from the seven bridges of Königsberg, although there are only four here pictured. So it's also an undirected but a non-weighted graph. Weighted or unweighted, we use these based on what you want to achieve, what sort of problem space you want to model. Okay, so moving on. So what's a graph database? It allows us to model this, to store edges, which can be called also nodes, and vertices, which would be the relationships or the lines in a graph. Both the nodes and the relationships can have attributes. So in the previous case, the weights on these lines would be the attribute. It would be one attribute. But there could be lots of other attributes like the label of that relationship, special properties of that relationship. If you could even say, if you had a directed graph, the direction of the relationship could be an attribute as well, I guess, loosely defined. So why do we like graph databases? It's conceptually and syntactically easy to traverse a large number of connections, a large number of relationships, and that's useful in certain areas. Now, the performance aspect here depends on the underlying implementation. So Neo4j, for instance, likes to boast that it's one of the few graph native databases. So it's graphs all the way down, as they would say, while this could also have been done with a relational database and then an abstraction layer above it that would handle this and translate this. So about Neo4j, first version was released in February 2010. It's written in Java, Go Java. It's ACID compliant, and it can scale. It uses the master worker model. So similar to the Solar server I mentioned the last time we talked, you have a master node. All writing is done to the master node, and you have the worker nodes that are continually pinging the master node and asking, has your data been updated? And if yes, it gets the delta, it updates, syncing with the master, and then you can use these replicas or workers for querying. You don't write to them, but you can use them for querying, thereby lessening the load on the master node. So it's using an open source graph query language that's called Cypher. I think it's safe to say it's at least a fourth generation. Yeah, it's a fourth generation language, so it's supposed to be closer to human speech, similar to SQL. I think if you know your way around SQL, you won't have any problems using Cypher. I didn't sleep much, but it took me about a week since I started learning to passing the certification for Neo4J. So yeah, it's not that hard. And here's an example of Cypher. So what does this query do? It says find all the products that either belong to a category called dairy products or are a subcategory. So one of their parent categories is called dairy products. And now next I'm going to show, this is an example of that same query executed using SQL. Looks a lot more verbose, messy, more places where you can make a mistake. Now, this came from the official Neo4j website, so I think we could optimize this maybe a little. I'm not sure. I can copy paste this later somewhere in a Slack channel if someone wants to take a go, make this a little better. But they do make the point that yeah, if you're going deep in these nested relationships, it's easier to do it like with a graph model. Any questions so far?
By using, so this is a newbie question, but by using an ORM, would you need to have this big of an, I'm going to say SQL, obviously ORM doesn't use it, an SQL necessarily. So would an ORM solve that or not?
I've experienced with only 2 ORMs. I would say no. But also with the ORM, you'd be very, very limited in any performance tuning that you'd be doing for this query.
Of course, that's the general problem of ORMs, yeah.
Yeah, I mean, okay, so you have an ORM, so you'd have like let's say if you're talking in Java, you'd have a POJO, and you have these nested relationships. Yeah, that's an interesting question. I know I need to take a look at that to answer with a greater degree of certainty. Anybody else? Okay, so I'm just going to move on to part 2. So part 1 was pretty brief, just short theoretical overview, and we're going to take a look at the 2 use cases now. So the first one, law enforcement, loosely termed, because it goes down to basically any area of government, also intelligence agencies. They all have a similar need here. But the basic idea is you have these agencies within the government that are tasked with regulating and enforcement. They all have their own information systems, which are a little bit different because they're modeled according to their responsibilities. So you have what's called the siloing of information. So they might be keeping records about the same person or organization or property or whatever, but they're in different databases. You don't know that they have them, and they might each be tracking different aspects of that object, right? So in a security context, it means that crimes are more easily committed. Also, they're less likely to be successfully prosecuted because you can't see the whole picture, or even it's harder to predict them because you can't see the whole picture in an easy and speedy manner. So I guess Americans might think of 9/11 now for a good reason, because I've seen, if I remember the rationalization around the Patriot Act and the later changes in legislature with the respect to the function of intelligence agencies, actually did use this argument about the siloing of information, that it made it more difficult to, so that there were indicators that an attack was coming on 9/11, but that they were spread across these various silos, so no one could put them together. I don't know if you'd like to comment here. Okay, so an example here is organized crime. It's difficult to police for a couple of reasons. One, they can't provide long-term support to their members. So, you don't know all the members. Someone is in jail, the other person could pay for a good lawyer. We've all watched the movies, seen that happen. And there are many other examples of this support occurring. Another one is simply because you have a group, which you may not even know all the members of this group, they can disperse their activities, the criminal activities, across the group, and this lowers their profile, right? So it's like, I don't know, if you steal a cup of, I don't know, a cup of oil versus taking 50 liters of oil, you know, person by person, or hauling it off at once. Just a bad example, but you know, that's the general drift. But yeah, so I'm gonna move on now to show how graph databases can help in solving these issues. So yeah, the graph solution here. So basically, the graph database here would serve as like a second layer. These databases would continue to operate on their own, but you'd have you know, like ETL pipelines, let's say transformation pipelines, that would run, and they would take data from these various databases and merge them all into the graph database. So you'd get what in marketing they like to call, in those marketing databases, the golden record, right? So one object here, be it a person or organization or a real estate or whatever, you get all of these data points from the various databases merged, and you could see them all in one place. So this would be both civil records, like addresses and financial records, along with police records, arrest records, surveillance records, whatever. And here's where, you know, network theory comes in well. So you can use this, which is a relatively new branch of I guess, in social science, based network theory, maybe, you know, 20 years in the making. But I'm not an expert here. So you can identify persons of interest in a couple of ways. One of this, of course, is kind of like you have a proximity score. So crimes occur. You know, some of the people that committed these crimes, or some organizations that are linked to them, you know, who got out of jail recently, who did they talk to. So it's possible to, you know, assign scores, and then based on that, you can say, okay, let's also take a look at this person who you might not have looked at before. You know, there might be something going on there. He might be working with them. And it's shown success in the field that in identifying suspects. And the other is, which is really cool, in my opinion, is this idea of the implicit social network. So basically, if you're not wearing a uniform, you don't have an ID that says I belong to the mafia or whatever, how would you figure out that somebody is working for the mafia, right? So, and you have all these things that are happening, all these data points being generated. So it allows you to infer with greater or lesser degree of certainty that two people know each other and work together, or, you know, come into contact often. You can start to theorize that they may be working together, especially if it's not an explicitly officially defined relationship. So you're looking at that. Any questions here?
Yeah, so basically, you said that they were importing like regular databases into the graph databases, but if they, for example, one of them didn't have a location of the suspect where he was moving or whatever, that wouldn't help them, right? Because they couldn't connect these two persons that they were, I don't know, walking around or driving through around same block or whatever to find the connection between them. If they don't have the similar data for all the persons that are in these databases, you would basically not have any mean to connect them, or?
Well, I think I understood the question, but I'm going to do my best to try and answer it. Okay, so you're talking about someone who has not been the subject of a criminal investigation before. There's no reason to track that person in any way.
Yeah, so basically to be able to connect two persons or two whatever, you have to have similar data for them. Otherwise, you are not able to connect them. But like you said, these agencies were importing their databases into this graph database to try to find the connection between the criminals.
Yeah, of course. So this would be a step before you start to track those people, but you might figure out that they went to school together or went to a juvenile facility together, that they have other points that connect them, that they own property together. I don't know, maybe somebody's a second cousin or father-in-law removed twice, whatever. The way you construct these models is up to them. So proximity here should not be taken only in the sense of geographic proximity. But yeah, I mean, I won't go into, I don't know really, I won't go into all the, what is actually being tracked here. So, but yeah, there are other ways other than, knowing their location throughout the day to make connections between people. And of course, this would not mean go and arrest that person. It would mean start paying more attention to that person. Any other questions? Okay, so that's the basic idea around law enforcement. I'm going to move on now to the second one, which is fraud. Well, yeah, and just here's an example, an illustration about the law enforcement idea. So, one thing I think I read that Google did and Apple did allow, if a crime was committed, to pull GPS data, around the time it occurred. But that was like an old article. I don't know if that was still being done. You could also ping the not the ISP, but the telco in question to give you triangulation data from their cell phone towers, I guess. So you could get some kind of geo data on people that weren't being explicitly surveilled. But this, I mean, yeah, I don't know about Croatia. I read this about being an issue in the US, but it was more in the context of helping absolve someone later that was wrongfully convicted or something like that. But that's the basic idea. So you have these three silos, they're merged together, you have the golden record. And yeah, you have these. Okay, so moving on to fraud. So fraud detection and the areas of interest being e-commerce, of course, so buying stuff online, banking, finance, insurance. And here are some common cases. So one is the drawing of multiple loans on already burdened collateral, which means I have a house, I take out multiple mortgages at multiple banks. It's not a package deal. It's not a legal refinancing. They don't know about each other. So I'm getting a brand new mortgage for all of these, for that one house in all of these banks. Right. The other one, fake identities for purchase and lines of credit. I'm a bit more skeptical about this one. I think in Croatia, it's much harder to make a fake identity and get credit based on it. But I have seen startups springing up that allow you to basically buy on like a pay later scheme, even though they're halfway across the globe from me. So maybe it's easier to trick them. And the third case being insurance fraud would be fake damages and injuries. And the white paper I read specifically said that soft tissue injuries are the biggest problem here, because it's really difficult to prove that no, this person is not in pain, so nothing has to be broken. It's I guess you can look for subcutaneous hemorrhaging bruises, stuff like that. But anyway, it's based on the doctor's report, subjective feeling of pain, blah blah blah. So it's easier to cheat there. No, you don't need to actually hurt somebody. And so the common thread here, how to deal with these cases of fraud, is to identify the same origin for seemingly unrelated requests. And of course, so investigators look here at, for instance, IP addresses, geographical addresses, contact information, and identities that repeat across different roles in different combinations. Right? Each one has a piece of the puzzle. And so here's an illustration here. So one thing that's useful to know just before I talk about the picture is the main problem in these fraud cases are not the lone individual, because it's easier to find him. It's these so-called fraud networks or groups, so that band together to commit crime, because they can mix and match real pieces of identities with fake ones and hand them off to each other because they're doing it voluntarily. I'm going to let you use a burner phone I have, and you can confirm it with an SMS. I'm going to let you put in my address there, and you can use my PO box. And so they trade these information points between them, creating fake identities. But each of these data points could be real, right? And you would need them to be real to collect some of the gains with this criminal enterprise. But it's hard to figure out that they're all working together, because you need to figure out the connection. So also important to note here, as was detailed in this white paper, is because you have these different aspects combining together, and you can maybe visualize it in matrix form, but you get, as the number of co-conspirators increases, you get what is known in mathematics as a combinatorial explosion. So these facets kind of multiply at a large rate, and it's difficult to track this when you have a large group, and also the financial gain increases as the number of people increases. So here you have, this is the first, this would be the second case already mentioned on those bullet points. So the fake identities, e-commerce fraud. So none of these people are real, but the data points are real. It's actually, these 4 people are actually 2 guys living on these 2 addresses, and they have these 2 phones, and the rest they're making up as they go. And they can, so in shopping situations, when you do get some kind of line of credit, they can max that all out simultaneously and run away. Basically, that's the idea. I mean, run away. Cut ties with these identities. Investigators will go to the address. Never heard of the guy. Nobody lives here by that name, right? And they're forced to write off this as a loss.
Is this like still a problem, or people solved this?
I have no idea, since I mean, what I know about Croatia, I think it'd be difficult to pull something like this off. I have no idea what's the US experience. But the thing about the combinatorial explosion is right when you look at the numbers. But it will be better shown in the second example with the medical fraud, the insurance fraud. So moving on to the second case, which, oh yeah, here's an example of that case, loosely modeled with the graph database. And here's how visually you can see that, okay, something is converging here around this address. And the idea is basically to look for these hotspots and to pick out the real data from the fake data. And then you have enough to identify the actual person that's behind these identities. But this will also be shown. So this is an example of insurance fraud, where you have people colluding together, a fake victim, a fake person who committed the accident. I'm not sure of the formal term. And a real doctor that's lying, and a real lawyer that's also lying. So they work together in groups, and so basically, they can pull in these. They're not big claims, because, as I said, so these are soft tissue damages that nothing broken, no disability, permanent disabilities probably, and stuff like that. So they're low-level claims, but if you have enough people, you can churn these out and make a nice amount of money. And you can see here also with these people. So this is just 5, 6 people. But as the number grows, the number of these interactions, you get this what I talked about, this combinatorial explosion. And so all of these people, so let's say person number 1, we're talking about so this line of people here, these black silhouettes. So this guy will be a witness here, a victim here, the perpetrator here. And again, so mix and match of roles, right? In these cases. So we can again model this in a graph. And so you figure out, okay, so there's something, so these guys that are going to this adjuster or this doctor, they're kind of, so this guy he was hit here, but then he witnessed here, and then he was a passenger here. That's, it goes beyond, bad luck or, random chance. So in the very least, you can pay more money to a private investigator to closely observe that person, hopefully catch him in the act in the second attempt to another insurance fraud. Any questions here?
So in order to find these hotspots, I assume it's similar like in SQL, you would do a, I don't know, something and then order by that column. Is it similar?
I mean, I didn't get much into that part by myself. I mean, you have models for assigning these scores, and then you'd, I guess, there are more approaches. They're even using machine learning, but yeah, you have some kind of formula depending on drawing from this like graph theory and network theory, what you want to measure. You construct a formula and you'd populate the data from the graph database. But I'm not an expert here, so yeah, you might be looking at the number of relationships or the type. I mean, you could just see, does this person appear in all of these reports, or how many reports, and then that's just for this one person. But if you want to find out the group, then you need to cross-reference, and I guess here the graph database does this more easily, because you can then say, so the person who was a relationship witness, and a relationship drives, relationship passenger, is connected to somebody who is relationship doctor, but was also a doctor for another passenger, and then you'd get a list of people that are kind of crisscrossed together.
Got it.
Any other questions? I think that would be the end of my presentation. Here, the next slide is just sources. Besides some Wikipedia stuff about general graphs and graph databases, I use these two white papers, which are available on the Neo4J website. You just need to fill out a form. They won't spam you. You can say you don't want to get mail, and that's it. And they go into much greater detail. And I think, especially in the graphs in government, it's not just law enforcement. They talk about everything from supplying troops in Iraq to, I don't know, supply chains across the globe and whatever.
Cool. Great. Thank you. Obviously questions now, but I'm curious, how does GraphQL fit into all this?
I'm not sure it does, at least not in Neo4j, but it's, as far as I understand, GraphQL is more like an abstraction layer than that you could have other types of databases below it, but I'm not an expert here.
I could say it doesn't have anything to do with graph DBs. It's because that's on the other end of the backend. That's an alternative to REST.
Got it. I'm actually back and forthing for the past 2 months with the CEO of Graph, how are they called? Hasura.io. They do this GraphQL something. So fingers crossed that we actually get the training on that. Of course, who's going to be interested? Cool. Guys, any other questions for Ivan?
I think this is really cool. I think it actually, in a way, kind of makes some sense for like what we do at the command center here. Because we could get you could get a call from somebody and we can audio fingerprint it, right? And through the magic of graph database, what are all the other phone numbers that have sent out a message with that same fingerprint, and then all of the different feedback from those phone numbers. It's quite a graph right there. Anyways, just gave me something to think about. Thank you.
Yeah, quite a bit.
Cool. Anybody else? Okay. In that case, thank you very much, Ivan. Everybody else, you are also invited to do something similar. So please. Cool.